Hey everyone, so let's solve this Leetcode hard problem, a minimum number of removals to make mountain array. So before moving on to the problem statement, I would like to say we will be discussing the most intuitive a pure DP approach that one can think of. Then we'll be trying to establish the DP, then we will see the transitions for means you but just based on the problem statement what we are required to do. We'll try to do it just by using DP, and then we'll be solving it, means seeing the standard approaches that are already present. Okay, so let's see the problem statement here. So we are given an array ARR which is a mountain array if the length of ARR is greater than or equal to 3 and there exists some index I. So there exists some index I which is greater than or equal to 1 and less than or equal to n minus 2. Okay, so it is lying in the middle of an array such that means all the elements before this index I are in increasing order. Okay, strictly increasing order, and all the elements after this I are in strictly decreasing order. So this ith element is the peak and means the elements are present in this fashion. So if there exists some index I for this given array, then it is called a mountain array. Now we are given an integer array nums. We need to return the minimum number of elements that we need to remove to make this given nums array a mountain array. That means it should become in this fashion. Okay, and the length of nums can go up to 1000, and we are given that it is guaranteed that we can make a mountain array out of this given nums. So for example, if we have the nums as this, so the element 1 is here, then element 3 is here, and then again we have element 1. So we see it is already in this fashion. Here this index 1 here is already following the fashion that before index 1 the elements are in increasing order and after index 1 the elements are in decreasing order. Okay, so hence this nums array is already a mountain array. So hence in this case we will not be deleting any elements because we need to return the minimum number of elements that we need to remove. So in this case we will not remove elements because this is already a mountain, and hence we will simply return 0. Let's see another input. So we are given the elements in this form. So the elements are, suppose we have 2, then we have 1, then again we have 1, then we have 5, then we have 6, then again we have 2, then we have 3, and then again we have 1. Okay, so this is the current structure the given nums array that has currently. Okay, now we need to remove some of the elements such that it becomes of this fashion, right? There exists some index, means there exists a single peak only, and all the elements on left are in increasing order and all the elements on right are in decreasing order. So how can we make this peak? So we know what means what problems are there currently. So if we see if we try to remove all the dips here, so if we try to remove this element as well as this dip here, so we'll see what will the peak look like. It looks like we'll go from 2 to 5, then 5 to 6, and then from 6 to 3, and then 3 to 1. So if we remove these 3 elements here, then definitely we are going to get an increasing, means get a mountain array. So in this case we'll be removing 3 elements. Let's see if there are other ways of doing it. So if we remove this 2 and this one, so in this case what will peak look like? We'll move from 1 to 5, then 5 to 6, then again we need to remove, means either 3 will be removing or 2 will be removed. So if we remove 2, then if we remove 3 suppose, then we'll have from 6 to, we will go to 2, and then from 2 we'll go to 1. So again in this case as well we have removed this 2, this 1 and this 3 to get the final array as what? Final array was 1, 5, 6, then 2, 1. So this is also like a mountain array. So hence the minimum number of removals that we need to do in this case to convert this into a mountain array is 3, and that is the minimum possible, hence the output here is 3. Okay, so based on this, what can be the most naive way of solving it? So we know since we need to remove some elements, so hence each element has a choice of either getting picked up or getting removed. Okay, and it will only get picked up if it is part of increasing subsequence, then it should be greater than the last element picked. Okay, and if it is if it is greater, means smaller than the last element, then it should be part of the decreasing slope. So it can only be picked up if it is greater than last or less than last, and if it is greater than last, then it should be lying on the increasing slope currently, and if it is less than last, then it should be lying on the decreasing slope. Okay, these two conditions are there, or else we will simply remove it. So each element has this choice of either getting picked up or not getting picked. So based on this, can we like what algorithm can we try initially? So we can simply like initially think of this DP. Okay, so what you'll do, we need to think in the direction of DP. So what you'll need to do, we need to iterate through all possible starting pairs ij, and then let the recursion decide whether to continue means climbing or start falling. Okay, so how will this DP state look like? So suppose if we are at a particular index currently, then what information do we need? We need to know what was the last element that we picked. Okay, then only means if this was the last element that we picked, then on the basis of that only we'll be able to decide whether the current element is greater than last or less than last. Okay, so we need to know, means we need to avoid those conditions where the current index is equals to last, because we cannot pick equal element in any case. Okay, so we definitely need this info about the last element that we have picked. So we'll maintain this info as well. Okay, so based on the index we will be getting this last. Now there can arise two conditions. If this error of index is greater than error of last, then we can only pick this error of index if we are currently looking for increasing slope. Okay, if we are currently looking for increasing slope, so we need to know whether we are currently on the increasing slope, means we need to maintain some value that currently we are looking for increasing slope, or currently whether we are looking for a decreasing slope, because we will be able to put this one. If this is the condition, error of index is less than error of last, then that means will be able to include this if and only if we are currently looking for the decreasing slope. So we need to maintain this information as well, whether we are currently on the increasing slope or whether we are currently on the decreasing slope. So hence we need a flag of suppose 0 or 1. Okay, so suppose 0 denotes that currently we are on the increasing slope, and 1 denotes that we have already encountered the peak and now we are looking for decreasing elements. Okay, so we need these two, means these three parameters are changing here. So what are the parameters? The index can go up to n. Okay, the last value that we have chosen can also go up to suppose n, and these values can means either be 0 or 1. So we need a size 2. So this is the DP size that we can create. We can create a DP of size n cross 2. Now this will be the index, means we have reached this particular index with this, means the last element chosen as this element, and 0 denotes we are at increasing slope, and 1 denotes we are currently on decreasing slope. So if we are currently on increasing slope, then we'll be able to pick if the current element is greater, and if we are on a decreasing slope, then we'll be able to pick the current element if it is smaller than the last element. Okay, so I hope the DP state is clear, how we try to make this DP based on like what information do we need to satisfy the requirements that we need to fulfill. Okay, now once this is clear, let's try to see the base case that we'll be having. Base case. So how will we, means what is the initial situation? Initial situation is we need to have, means before moving on, let's see the initial situation. Okay, how will we call the memoization function? Okay, how will we call the memoization function? So we know like we need to choose some element before, okay, so that this last is valid. Okay, so we'll definitely need to fill this last with some value. So we'll definitely need to choose some element for this last and then call the index with last plus 1. Okay, and currently we are looking for 0 slope. Okay, we are looking for increasing slope. But why, means why only choosing the last element will not be feasible? Because suppose we picked an index as last and then we are currently on this index, okay, which is this was the last index and we are currently at this index and we are looking for increasing slope. So at each step the memoization will not care whether, means will only check if the current flag is 0. We can also will be writing the code that either will keep increasing or start decreasing, means the last was the peak, now we start decreasing from here. Okay, so based on this index, means we'll not be able to know whether, means the memoization will be performing all those functions, right? So hence if we have this last index here and we perform this operation, that if this last, means current value is less than error of last, we'll simply perform, means this flag will change from 0 to 1. Okay, now we are looking for decreasing slope. So if we do this, then we see like we did not got any left portion, right, for this peak. Okay, so we need to make sure that there exists a valid left portion, then only we can move downwards, right, then only we can start a decreasing slope. Hence only picking the values for this last will not be valid. Okay, we need to look for all pairs of ij, and if this nums of j, suppose nums of j is greater than nums of I, then what we'll do, we'll make this last value equals to I. We picked this nums of I as the first element. We picked the last element that we picked was j, and we'll call the memo function with j plus 1. Okay, and the last value was j, and currently we are looking, means we are on the increasing slope. Now since we have already picked up two elements, now even if we do the decreasing slope, we'll be able to know, like, since this portion already exists, we'll be able to perform this means downward operation, downward slope thing without any means checking for any condition whether it is the first element getting picked up or not. Okay, so hence we need to iterate through all possible pairs of ij and see like whether this nums of I is greater than nums of j. Okay, nums of j is greater than nums of I. So if nums of j is greater than nums of I, then this will be the last element that we picked. This was the second last element, so we'll not be accounting that in dp. Or obviously if we have the I and the j, so we picked these two elements, nums of I, nums of j, and we are calling the memo function for j plus 1. So we know like the number of elements that we have removed from this section was, in the section from 0 to j, we only picked how many elements? We picked two elements. Okay, we picked two elements. So number of elements that we have removed, number of elements here is j plus 1, and we only picked two elements. So number of removals that we have done is j plus 1 minus 2 equals to j minus 1. Hence these many minimum means removal operations we have already performed while we are choosing these two pairs of nums of I and nums of j, and then we are calling the memo function for what? Memo function for the next index, which is j plus 1, and the last chosen index was j, and we are currently looking for means the increasing slope. Okay, so this is the index, this is the last, and this is the flag of increasing or decreasing. Okay, so now what we'll do, we'll simply loop for this I from 0 to n minus 1, n minus 2, n minus 1, 2 suppose, and loop for j from I plus 1 till n minus 1, and this will also go till n minus 2, so that we have a value, means this should go till n minus 3, so that this j goes to n minus 2, and we have still an element which can act as a downward peak, because we do not need a mountain array like this. This will not be a mountain array. We need to have a decreasing slope as well. So now we'll check whether nums of j that we have is greater than nums of I, then only we'll be able to call, means the number of removals that we have done in this case. So we'll maintain a mini, means min removals, and initialize it with suppose a very large value, suppose n. Okay, now we'll be updating this min removal value with the minimum of already calculated min removal and the number of removals that we have done currently. So number of removals was j minus 1, plus we'll be calling the memo function. Okay, so we'll be calling the memo function with what values? We'll be calling the memo function with j plus 1 with the last value as j, and currently we are looking for increasing. So I hope how means this last as well as means with the condition of this is avoided, means consideration of this is avoided, making a mountain like this. So by initializing both the values, means initially picking two values initially only, then we will be able to avoid these two conditions. Now let's try to see the base case as well as everything. So we have called this memo function. So memo function has what? It has the index, it has the last, as well as it has the suppose flag. Okay, so now when this index reaches n, what will be the case? What will be the base case? So when this index reaches n, we want to make sure that this flag had become 1. Okay, it is not still 0, because if it is still 0, that means we are currently on the increasing slope one. But in the end, what do we want? We want to end it on a decreasing slope, so that there is exist a peak. Okay, so hence if this means if this flag is equals to 1, then only we'll be returning means 0 value. That means this is a valid ending. But if this is still 0, that means we are on the increasing slope. So hence we need to return a very large value so that this minimum that we are doing at each step, it becomes very large. Okay, so this doesn't happen. So in that case, what we can do is we can simply return n here. Okay, that means we need to remove n elements. So if we have reached end of the index, end of the array with flag 1, that means we are on a decreasing slope. We picked some elements and we are on a decreasing slope, and we can simply return 0 in this case. Okay, now once this is clear, we have two cases. Either the first case will be to simply skip the current iteration. Okay, so if we simply skip the current iteration, that means it will be simply what? We'll again call the memo with index plus 1. The last remains the same, as well as this flag remains the same. Okay, and skip means we have removed one element. So we'll be increasing the number of removals by 1. Okay, because dp stores what? It stores the minimum number of removals that we need to do till this index with the last chosen element as last, and we are currently looking for the increasing slope or decreasing slope. So in the skip case, what we will do? It will be simply 1 plus memo of index plus 1 last and flag. So this will be the number of removals in the skip case. Now the case of picking. Okay, so picking can be done either on the basis of if we are looking for the increasing slope or we are looking for decreasing slope. So if the flag that we have is 0, if this flag is 0, that means we are looking for a increasing slope currently. Okay, so if we are currently looking for increasing slope, that means we need to make sure that currently the nums of index that we have, it should be greater than the nums of last. Okay, this condition should be satisfied. Now if and only if this condition is satisfied, then only we can pick pick the current element. Now again there exist two choices. There exist two choices of what? There exist two choices of if this was the last element and this is the current element. So either means after picking this particular index, we can start looking for a downward slope, or we can keep looking for the increasing slope only. So we have these two choices as well here. Okay, so we have means if nums of index is greater than nums of last, so we'll have two choices. Either we'll be calling the memo function with one, means we'll not do any removal. So we'll call the memo function with what? We'll pick this particular index. So it will be what? Index plus 1, and the last becomes as index, and the flag remains the same, means we are still looking for increasing slope. Or we can also call it as memo of what? Memo of index plus 1, index as well as 1, means now this index that we have chosen is the peak, and now we need to look for a decreasing slope now. So we'll call, means in this case we'll get able to call both of these memo functions. And else if the flag is already 1, that means we are looking for a decreasing value. Okay, so we can only pick the current value if this nums of index that we have is less than nums of last. So if the nums of index that we have, it should be less than nums of last. So if this condition is satisfied that the current nums of index is less than nums of last, then we'll simply call the memo function with what? Memo function will be called with index plus 1, index, and flag still remains 1 as 1 only. Okay, so flag still remains 1 only. And in the end, we will take the minimum of all possible these values to update our current DP, and that is how the DP will be updated. So I hope the true DP nature of this problem is clear. Means we have means if you try to see other solutions, you will get like the standard approaches of trying to relate it with direct relating it with longest increasing subsequence and longest decreasing subsequence. Okay, but means analyzing it purely on the basis of what were the requirements, and then analyzing the true states of DP, and then trying to see the transitions on the basis of that was I think was pretty important, and that's why I tried to explain this approach here first. So I hope the transitions as well as how we are calling, means how we are already picking the two elements to avoid any failure cases is clear. Let's try to see the code once, so that this approach becomes much clearer in general. Okay, so what we'll do initially, we have initialized the DP with what values? We initialize it with 1000 cost 2, because n can go up to 1000 all. Okay, so we have initialized it with global DP so that we do not need to pass it in function every time. So we have initialized as well as array and n we have also made it global. So we initialize all the DP with -1 values. We mark it the ARR as air nums and n equals to nums of dash. Now the minimum removals that we need to do initially is equals to n. We'll iterate through all possible starts of the mountain. So I equals to start of the mountain and j equals to second element of the mountain. Okay, so this is the I, this is the j. So I will go from 0 to n minus 3, j will go from I plus 1 till n minus 2. Now if nums of j is greater than nums of I, then I was the first element, j was this element, this is I, this is j. So we have already picked two elements. Now we'll be looking for the increasing slope, and we can simply move to the decreasing slope by skipping. Okay, so this is possible at every step. So what we'll do, the number of removals that we'll do is simply from 0 to j, we have removed two elements. So we have only picked two elements, other elements we have removed. So it is simply j plus 1 minus 2, which is j minus 1. So it will be minimum removals will be updated with minimum of j minus 1 plus the memo function will be called for j plus 1. The last element was j, and currently we are looking for an increasing slope. And in the end, we'll simply return this minimum removals. Okay. Now let's see the memo function that we have. We initially see the base case. Flag equals to 0 means we are currently on the increasing slope, and flag equals to 1 we can currently on the decreasing slope. Now we have the base case. When we reach the index n, if flag is equals to 1, then it means we have ended at a good node. That means we are able to find a decreasing slope and we have chosen some element. We will simply return 0. Else we return a very large value so that this minimum value becomes very large and we are able to avoid that case. Okay. Now we'll see whether this state is already calculated. So we'll simply return it. Else the first case is to simply skip the current element. So we'll simply skip it. That means we are increasing the removal count by 1 and call the memo function what index plus 1, last remains the same, flag remains the same. Now the second option is to pick the current element. Okay, so for picking what we'll do, the first case if flag is 0, that means we are looking for increasing element. So we'll keep looking for increasing element. Okay, so we'll keep looking for increasing element. In that case what will happen, if error of index is greater than error of last, so we'll keep looking for increasing element. So we'll call for index plus 1 and we'll look for 0. Now either if we keep looking for increasing element, or if the error of index is less than error of last, then we can pick this as the 0th element, means pick this as a part of decreasing slope and start looking for decreasing element. Okay, decreasing slope. So we can do that. Or if it is already a part of decreasing slope, then we can simply continue doing the same. And in the end, we'll simply return our result because we have taken minimum at each step. So this will be like the overall means discussion on the pure DP approach. Means we see the time complexity of this will be of the order of n square, means 2n square, and yeah. So this will means because the overall DP calculation that we need to do, means overall it will be n square into 2. Okay, so this will be like the overall time complexity of this approach, and it will be like fine given the constraints. So let's try to submit this approach here and see how much time it takes to run. I know it will take a lot of time to run because obviously this is not the standard approach, and means all the solutions that already exist is pretty fast. Okay, it is like only beats 5% of a solution, but this solution was like pretty useful to means get an idea about the problem statement that we have. Okay, now we'll be moving on with the standard approaches that we'll be using to solve this. So once this DP approach, I hope this DP approach was clear and you were able to see this problem from a new perspective. Now the final means the standard approaches is to simply use LIS or LDS. So what is the approach? We can see each index, we visualize each index I as what? As the peak. Okay, so we want to make the nums as what? We want to make it in the form of a mountain. That means there will be some peak. So we can visualize each I as a particular peak, and that means all the elements from left on its left will be a part of a longest increasing subsequence. That means the longest increasing subsequence that we can get on the left till the ending at this index I, and on the right it will be longest decreasing subsequence starting from I. Okay, so what do we want to find for this each I? Will we find LIS of I will be simply longest increasing subsequence ending at I. Okay, and similarly we'll be able to find LDS of I as longest decreasing subsequence starting at I. Now if we have already know about these two values, LIS of I and LDS of I, so the means the number of elements that we will be picking For this case, it will be what? It will be LIS of I plus LDS of I. But in this case, we have picked this ith element twice. So we need to remove it once. So it will be 1. So this is the number of pick, means the maximum length, maximum elements we can pick. Maximum elements we can pick. So we can find the maximum of these, maximum for all I from 1 to n minus 2. Okay. So we can do this for all I from 1 to n minus 2, and it will be the maximum elements that we can pick. So since we want to find out the minimum number of removals, so it will be simply what? N minus this maximum value. Okay. So max pick it will be. So in the end, we will simply return this value. Now, how do we find this LIS or LDS? So I hope you have solved the problem of longest increasing subsequence, or are already aware about how do we solve, means how do we find out the longest increasing subsequence in a given array. So if we are already aware, then it will become pretty simple. I hope, like, if you are not already aware about it, then this approach we have already discussed. Then you can, like, first see and learn about LIS or LDS. Then, like, this will become pretty simple now. Okay, so how will we find this LIS? So you simply initialize a DP of size n, and where DP of I will be denoting the longest increasing subsequence ending at I. So obviously we know, like, we'll be initializing all the DP initially with size 1, because all index we can choose as a single element. Now how do we find out? So for each I, what do we want? For each I, we'll look for all j's from 0 to I minus 1 and consider them as the last element picked. Okay, so now if the current nums of I that we have is greater than the last, means this j that we picked, so this DP of j that we'll have will be storing the maximum subsequence, longest increasing subsequence ending at j. So we can simply update the number of, means longest subsequence ending at I with the maximum of what, which will be DP of j plus we have a new element. So we can update it with the DP of j plus 1 comma the already value that we have calculated. So we can update this with maximum at each step for all j from 0 to I minus 1. Okay, and in this fashion we'll be able to calculate the DP for each I from, like, 1 to n minus 2. Okay, in this fashion we will be able to calculate the LIS. And now for LDS we need to find out the longest decreasing subsequence starting at I. Okay, so since we want to find out the longest increasing subsequence starting at I, so we'll be starting this I loop from what? From n minus 1. Why? Because we need to know about the values on the right to calculate the result about this particular index. Okay, for longest increasing subsequence we wanted to move from 0, I moved from 0 to n minus 1, because for longest increasing we wanted to, it was ending at I. So we need to know about the previous occurrences, previous indexes to calculate the result for current index. But it is longest decreasing subsequence starting at I, so hence we need to know about the elements which are already occurring on the right. So it will do, it will move from n minus 1 to 0. Now we'll again have this j which will be moving from what? It can move simply from n minus 1 till greater than I. Okay, simply here we move from j to 0 to I minus 1. We can move j from n minus 1 to I plus 1. And we see, like, we have I here and j here. So what do we want? We want the nums of I to be greater than nums of j. So in this case, again we'll have the same loop, same logic here. If nums of I is greater than nums of j, then what we'll do? The number of, means the longest decreasing subsequence that we have got is starting at this j will be getting, means increasing it by 1 if we choose this ith element as well. So we'll have simply DP of I will be what? It will be DP of j plus 1, or it will remain the same, means we'll take maximum at each. Okay, max. So this DP of I will be able to calculate. So this will be the LDS. This is how we'll be calculating this LDS, and this is how we'll be calculating the LIS. So this is the pretty popular approach of finding LIS in n square. So if we are aware about it, then it is pretty simple. Okay, and once we have both of these values calculated, how we'll find the maximum result? So we'll find the maximum value of LIS of I plus LDS of I minus 1, and we need to make sure that there exists a LIS. That means the number, means LIS for this each I, we need to know that this LIS should be greater than 1, because there exists at least one element on the left, so that there exists an increasing slope, as well as this LES should be greater than 1. Both of these values should be greater than 1, means it should have at least two elements. then only, otherwise this is not accepted, or simply this is not accepted, right? So hence we need to, for each I, we need to see like whether this value is greater than 1, this is also greater than 1, and then only we'll be taking the maximum. Okay, so we can simply calculate these two values and find this maximum value at each step, and then simply return n minus max peak that we can do. So let's see this code for this approach, and then it will become much clearer. So we have the same LIS DP as well as LDS DP. LIS stores the length of longest increasing subsequence ending at index I, and it denotes the longest decreasing subsequence starting at index I. Okay, now we'll calculate the LIS starting from left to right. So it will be simply I moves from 0 to n minus 1 and j moves from 0 to I minus 1. If nums of I is greater than nums of j, we can pick the nums of j as last element. So it will be simply dp of j LIS of j plus 1. Okay, and simply we can compute the LDS from right to left. Move I from n minus 1 to 0, j moves from n minus 1 to I plus 1. And now this, if nums of I is greater than nums of j, that means this is a decreasing slope. So if this has some LDS, so it will be simply, means if we include this element as well, so it will become LDS of j plus 1. Okay, it will be increased by 1. So at least we will be calculating these two values. Now we want to find out the maximum mountain length we will get. So it will be simply, we'll move from 1 to n minus 2. We'll calculate, check whether both of these values are greater than 1, and if they are, we'll update our max mountain length with what? LIS of I plus LDS of I minus 1, because we have counted the peak twice in these additions, and in the end we'll simply return n minus maximum mountain length. So in this manner we will be able to find out the result in order of n square, and this is like a more intuitive or more standard approach compared to the previous approach that we used, and it was like pretty confusing as well, because we are maintaining flags and means the logic was pretty difficult. Means the DP is not pretty difficult, but like trying to code that approach, means thinking about that this approach is good, but trying to code it may take up a lot of time. So that's why we have tried to see this standard approach as well. So I hope this approach is clear. Let's try to submit this code here, and I hope like it will obviously beat a lot of time, because currently it only beats around 5% of the solutions. Let's try to submit this and see how much time it takes to run. Yeah, it beats 45% of the solution, since the complexity is still order of n square. Okay, that's why it runs in 60 ms and beats only 45. So you can see like there is a peak here of solution which runs in 2 ms and 6 ms. So maybe we need to think of some solution of a better complexity than this order of n square. So again, if we have used LIS or already know about LIS, you know like there exists an approach, means the n square approach that we have already discussed, but there also exists an approach using binary search to find LIS in n log n. Okay, so now we'll be discussing that approach to calculate the LIS as well as LDS in n log n, and then the overall complexity would be of the order of n log n, and that is what is expected based on these runtimes that we have. Okay, so let's try to see that. I hope you are already aware about how do we find means LIS in n log n. If you are not, I will give you a brief idea about it. So if we have the input, let's take a given input 2115623 211 2115623. So in the order of n square, the approach that we have, what we try to do is we look for all possibilities of the last element that we can pick, and then update our LIS or LDS DP. Right? We look for all possibilities of the last element and then update our DP. But in this, what we'll do, suppose we'll maintain a list of, means we'll maintain a temporary list which will be having the elements in such a manner so that the minimum element that we can have till index I minus 1 as part of the longest increasing subsequence is put at the end. So how we'll do it? So suppose we have the LIS vector initially which only has the second element, means the first element, which is 2. Okay, now when we reach at this, so obviously at each step how we will update our DP. So this is the DP which stores the longest increasing subsequence ending at I. So for this index it is simply 1. Okay, simply 1. Now when this value 1 comes, we see like this 1 is not greater than 2. So for this index, for the next index, which value is better to choose as the last index, whether it is 2 or whether it is 1? So obviously it is 1 because it is smaller than 2. So if we have a 1, means if we have a 2 in the next, we'll be able to get an increasing subsequence of length 2 instead of 1. Okay, so if means the current nums of I that we have is not means it is less than equals to what? LIS dot back, the last element present in the LIS. So what we'll do, we'll replace this means we'll find the first element, find first element greater than equals to this value, which is nums of I. We'll find the first element greater than equals to nums of I and replace that element with this value. In this case, the first element greater than equals to this 1 is 2. So this LIS will now be updated with what? With 1. And since the means this index is getting updated, so the length till this index is 1. So hence for this index as well, the longest string in subsequence starting at I is 1 only. Okay, now when we reach this one, we see again it is not greater than 1. So we cannot simply add it as a next element because it is greater than the last element. So again it is less than equals to LIS dot back. We will find the first element greater than equals to nums of I. So it is still greater than equals to 1 only. So again this LIS will remain the same only and we'll get the DP ending at this index as 1 only. Now when we have a 5, we see like this 5 is greater than 1. So we can simply push this 5 in the end. Okay, so we can simply push this 5 in the end. So this will be the LIS that will be getting 1 5 and of length 2. So hence the LIS ending at this index will be 2. Now we have 6. So again this 6 is greater than LIS dot back. Okay, so we'll simply push this 6 in the end. So if we push it, what will become? The length will become 3. Okay, ending at this. We can get it as this 156 or 156, or we can also get this as 256, but we know we replace this 2 with 1 so that we are picking the minimum value possible at each step. Now we have this 2. So what we'll do, this 2 is not greater than LIS dot back. So we'll find out the first element greater than equals to nums of I. So first element greater than equals to 2 is 5. So currently have the LIS array as 156. We find out the first element greater than equals to 2, which is 5. We replace this with 2. So LIS will become 1 2 6. Okay, and since we want to find out for this index ending at this index, so since we replace this element, so that means the LIS ending at this will be this length. Okay, so number of elements till this index, which will be 2. Okay, now we have this element 3. Again this element 3 is not greater than 6, so we'll be finding out the first element greater than equals to 3, which is 6. Update this LIS array with 1 2 3. And since we updated this element, hence the LIS ending at this index will be what? 1 2 3 1 2 3, and the length will be simply 3. And then again we have this LIS 1, which means is obviously not greater than LIS dot back, so we'll be updating this element, and since we are updating this element, the LIS will be of length 1. So this is how we'll be able to maintain this DP. How we'll simply find out the first element greater than equals to nums of I at each step, and then update that if it is not already greater than the LIS dot back. And how will you find it? It will simply be we'll simply find it using lower bound or upper bound. Okay, we'll simply use the inbuilt upper bound, or we can simply use the lower bound as well. Since we want a greater than equals to, so we can simply use this lower bound. And once we have, we'll simply be able to update this and we'll be able to get the result. So this is the a very popular approach of finding LIS in n log n. Now how we'll be using it? So what was the logic here? We wanted to find out this LIS as well as this LDS. So we'll be finding LIS in n log n using the approach that we discussed. Now we need to find the LDS here as well. So we can simply write a function for LIS on the reverse of nums array. So if the current nums array is 1 2 3, then we can find out the LIS in the reverse array 3 2 1. And if we find out the LIS in this reverse array, so we'll get the DP as what? 1, then 1 here as well, 1 here as well, because the longest increasing subsequence is of length 1. And this will denote the longest decreasing subsequence is starting at this index, is starting at this element 3. So at 0th index, the value will be for this second index. At first index, it will be the first same, and for first index means the 0th index, it will be present as second index. So hence, once we have calculated the LIS on the reversed nums, we need to reverse this as well to match the indices. Okay, so that this matches this, means this is the result for this. this is the result for this, and this is the result for this. Okay, so what we'll do for finding out the LDS, we'll simply find LIS of reversed nums and then reverse the result. Okay, reverse the result of reverse the DP result to means match the indices. Okay, and then we will simply use the same formula that we have. We will be using same formula. So let's see the code of L log n approach. This is pretty popular. Like I means if you are not able to understand much from here, like you can go through popular articles, because finding out LIS in N log n as well as this order of n square is like pretty important, and it may appear in a lot of problems. Okay, so I hope means this is a separate part of the problem. Once we are able to solve this, then finding means applying this in our already existing problem is totally different. So since already the video has been pretty long, that's why I am not discussing it in very detail. We'll be seeing the implementation, then like I hope it will become much clear. So we'll first find out the LIS. Okay, so how do we find the LIS function? So we'll simply initialize the DP with 1. We have this LIS vector, that we temporary vector that we created with the first element. Now if the new element that we have is greater than the LIS dot back, we'll simply push it, and the LIS ending at I, it will be simply the new size of the list that we have. Else we'll find out the first element greater than or equals to nums of I, which is simply lower bound, and we'll update the element present at the index with the new value, and the LIS ending at this I, which will be if we are updating this index I, then the length will be from 0 to I. So the length will be simply I plus 1. So since we are updating this index, then will be IND index, hence the length will be simply index plus, and then we'll return DP. So this is how we calculate the LIS in L log n. Okay, now once we are able to calculate this, we'll be utilizing that. So we'll find the LIS. Now we want to find the LDS, so we'll reverse the given nums, and then we'll be able to find out the LDS using the LIS of this nums. And now to match the indexes, we'll simply reverse the LDS vector as well, so that now it will store the LDS starting at each index. And again we'll use the same thing that we did here. We'll be using the same for each index from 1 to n minus 2. We'll find out the max mountain length, and in the end return n minus max of mountain. So this is the most optimal approach for this problem of the order of n log n. Let's try to submit this code here in the DP, and I hope it now falls in the leftmost range of getting accepted. Let's see. It runs as 0ms and beats 100% of the solution. So that's why this was the most optimal solution of this approach. So I hope you were able to follow along with all the approaches that I tried to discuss. Firstly, I tried to made you think in the direction of pure DP, because thinking in this direction was pretty fruitful here, because we are able to analyze different cases and how we try to make the DP based on the problem statement. So making the DP means the first step was pretty tough. Then we tried to analyze the transitions. Then the second part, tough part, was to find out that we need to pick these two elements initially only, because otherwise we'll be getting an increasing slope or we can get a decreasing slope. Okay, so that's why we try to do that, and then try to see the transitions and everything. Then we move towards the standard approaches of thinking each index as a peak and finding out the LIS ending at I and LDS starting from I. And then we try to build the formula and solve it on the basis of using two approaches to find the LIS in order of n square, and then the most optimized approach of finding LIS in order of n log n. So I hope the entire discussion was fruitful and you learned something new from here. And if you did, make sure to like as well as subscribe. And if you yet have any doubts remaining, feel free to comment down. I will be happy to respond. Thank you so much for watching.